We present Universal Deep Image Compression via Content Adaptive Optimization with Adapters. The authors are Koki Tsubata, Hiroaki Akutsu, and Kiyoharu Aizawa. We address a novel task that we named Universal Deep Image Compression. Previous studies in deep image compression mainly focused only on natural images. In contrast, our study aims to compress images in arbitrary domains such as natural images, line drawings, and comics. In addressing universal deep image compression, we encounter a problem that the performance of compression models degrades on out-of-domain images due to domain shifts. Here, we show an example of a comic image when pre-training a compression model on natural images. We can see that the result of WACNN is blurrier than that of VVC, even though WACNN is generally better than VVC on in-domain images. To address the problem, we propose a content adaptive optimization framework. Our framework adapts a pre-trained compression model per image to address domain shifts between pre-training and testing. We highlight the difference from a general image compression pipeline. The difference is the insertion of adapters, latent refinement, and adapter training. We explain each component in detail in the next slides. We explain the insertion of adapters. Adapters are modules with a small number of parameters and have been successful in parameter-efficient transfer learning. We empirically determined a good insertion position for adapters and inserted an adapter into the window attention module in the main decoder. We then explain the latent refinement. We optimize the latent representation in terms of rate distortion with gradient descent. We finally obtain the optimized latent representation. The latent representation is converted into the latent bit stream by entropy coding and transmitted. Next, we explain adapter training. We optimize the adapter parameters in terms of rate distortion with gradient descent. In this optimization, we use the optimized latent representation obtained by the latent refinement. We finally obtain the optimized adapter parameters. The adapter parameters are converted into the adapter bit stream by entropy coding and transmitted additionally. Here, we show the comparison with existing methods. We adapt pre-trained compression models to each target image to address domain shifts between pre-training and testing. Moreover, to transmit parameters for updating the decoder, we use parameter-efficient modules named adapters and optimize the parameters in terms of rate distortion. We evaluate our method in experiments. We construct a dataset of uncompressed images in 4 domains: natural images, comics, line drawings, and vector art. We use natural images in the Kodak dataset and images in the other domains sampled from the BAM dataset. We show the quantitative results in the table. We compared ours with a state-of-the-art conventional method, the baseline method without adaptation, and existing adaptation methods. The results indicate that ours outperforms these. We show the qualitative results. The results show that ours can reconstruct the brush texture better than VVC and WACNN. We further show other qualitative results of conventional codecs, the baseline method, and ours, on the 4 domains. Ours can reconstruct the original image with relatively high fidelity. For example, ours can reconstruct the wires, shadow of the character's head, overlapping lines, and the monster's nose, with relatively high fidelity. We conclude our study. We addressed a novel task that we named Universal Deep Image Compression. To address the problem of performance degradation on out-of-domain images, we proposed a content adaptive optimization framework. Our experiments on 4 domains showed that our framework outperformed the baseline method, VVC, and existing adaptation methods. Thank you for listening.